recall from a previous chapter when we talked about inverse functions that only particular functions have inverses which are themselves functions. And the functions which have inverses which are functions which are continually increasing or continually decreasing. Those are functions which pass a horizontal line test. So if we're examining the sine function, for example, to see if we'll have an inverse which is a function, then clearly we will not have an inverse which is a function because the graph fails a horizontal line test. Now, to remedy that situation and to be able to talk about the inverses of sine, cosine, and so on, we have to do this. We just have to limit the domain that we're talking about for our function. And we saw that situation as an example in the chapter involving inverse functions. But here's what we want to do. We want to limit the domain in such a way that we capture all of the range values. That is, now the range now for the sine curve would be from 1 to -1. Those are the y values that are on this graph. So we want to limit the domain of our sine curve or our sine function so that we capture every value from -1 to 1. So that means that we could define our domain to be within this interval because we capture all of the items from 1 to -1. You see, within this interval. And then we could talk about the inverse of the function defined within that interval. That's what I'm talking about. Now, we're looking for a convenient interval over which to define our function. And that convenient interval is right in here. It's like right here, straddling the origin. Now, this is pi over 2, and this is negative pi over 2. And within that interval, we capture all of the possible values for y. That is, our function takes on all the values from -1 to 1 within this interval. And that's an important idea in having a nice inverse. All right, so here's what we're going to do. We're limiting the domain to this. These aren't asymptote lines. Now I'm showing you where we're limiting the domain. So we're now going to redefine this, or we're going to say, okay, we're saying we have f of x is sine x, but the domain is from negative pi over 2 to pi over 2. So negative pi over 2 is less than or equal to x, and x is less than or equal to pi over 2. All right, now with that limitation, now we can start to talk about inverse. Okay, we've got our limitation. Now let's generate inverse. Remember how we did that before? It's a swapping of the role of x and y, and then a solving for y. Well, let's see. We think of this as y equals sine x. And now for inverse, we swap the role of x and y. So we write this as x equals sine y. And now the trick is to solve this for y. Well, gee, how do we solve that for y? Well, we can do it like this. We can think sine of y is just an operation on y. And if we can somehow undo that operation, and apply that undo operation to both sides of the equation, then we'll isolate y. All right, that's kind of a fundamental conceptual idea for dealing with this algebraically. And let's do that. And let's define that undo operation as an inverse operation. That's the way that they have operated before, that squaring and square rooting are inverse operations, you see, and they undo one another. Okay, so we're going to think about undo sine as inverse sine. We're going to designate inverse sine in a way that we have designated inverses before. And it's like this. Now, when I inverse sine on this side, I have the inverse sine of x. And on the right, I have undo sine. Well, the sine goes away, and I have simply y. Now, generally, we write this as y equals the inverse sine of x. Now, it's very important to understand what this means. This inverse sine of x is actually a request for an angle whose sine is x. You see, it's a request for an angle, or it's a request for a real number whose sine is x. Now, so we can think about it in those two different ways, and I want to make a unit circle here and a little triangle. Okay, here's our right triangle, here's our unit circle, and here's our angle. Now, we are looking for the angle whose sine is x. And I'm not thinking of an xy situation over here. I'm more thinking about a real number situation. Now, we also related the idea of angle with arc length. So we could say then that we're looking for an angle whose sine has a certain arc length. Now, because of that kind of relationship, a lot of times this inverse sine of x is written as arc sine, because we're looking for the arc whose sine is x, you see? So it's written as arc sine x. Now, these two mean the same thing. Inverse sine of x, arc sine of x mean the same thing. All right, let's talk about domain and range a little bit. Now, we understand that there is a nice relationship between original functions and their domain and range, and the inverse function and its domain and range. All right, let's think about that. What about the range for our original function? Now, we know the domain here. We limited the domain to negative pi over 2 to pi over 2. And that's like negative 90 degrees to 90 degrees if we're talking about degree measure. Now, what about for the range? The values that the sine of x can take on? Well, the range would be negative 1 to 1, remember? So it's negative 1 is less than or equal to y is less than or equal to 1. Okay, now, the domain of the original function becomes the range in its inverse, and the range of the original function becomes the domain of the inverse. So for our inverse function idea here, the domain of the inverse corresponds with the range up here, so it's negative 1 is less than or equal to x is less than or equal to 1. Now, what that implies here in a practical way and in using this notion of inverse is that we can only take the inverse sine or the arc sine of x values that are between negative 1 and 1. We can't take the inverse sine of 3, for example. You see, so that's what the importance of the limitation of the domain is. All right, now what about range? Now, the range of our inverse corresponds with the domain of the original function, and that domain was limited to negative pi over 2 to pi over 2. So the range here is from negative pi over 2 to pi over 2. Now, here's what that means. That once we take the inverse sine of these x values between negative 1 and 1, what we come out with are angles. And those angles fall between negative pi over 2 and pi over 2. And from the standpoint of quadrants, we're talking about, well, let's look at quadrants. Here's pi over 2. Here's negative pi over 2. So from negative pi over 2 to pi over 2, we're talking about these two quadrants. You see, so when we perform this operation of inverse sine, we're going to get answers or angles that fall in these two quadrants only. Now, we'll deal with other situations, but we need to realize that from the very beginning. All right, and this corresponds to negative 90 degrees to 90 degrees. Okay. Now, remember that we talked quite a bit about the sine and other trig ratios on some particular angles. And if we're talking about first quadrant situations, then the sine of 30 degrees was 1/2. The sine of 45 degrees was the square root of 2 over 2. The sine of 60 degrees was the square root of 3 over 2, and so on. Sine of 0 degrees is 0. The sine of 90 degrees is 1. And we have counterparts in the radian world as well. You see, and we can either think of these as angles in radian measure, or we could think of them as real numbers. But at any rate, when we take the sine of them, we get the same values that we get over here in dealing with these angles measured in degrees. All right, now, let's keep that in mind when we work problems like this. We want the inverse sine of the square root of 3 over 2. This is a request for an angle or a real number whose sine is this value. So we come over here to this list and we look for the square root of 3 over 2 as the sine of some angle. We see it here, we see it here. So the sine of 60 degrees is the square root of 3 over 2. So the angle we're looking for is 60 degrees, you see, or it is the real number pi over 3. So the answer here is 60 degrees or pi over 3. A similar request is made using the arc sine notation. Arc sine 1/2 means we're looking for the angle whose sine is 1/2. So we go back over here at our list, and I'm not presuming that we could recall this. We may be able to at this point, and we will be able to later probably, but right now we may need to have a list like this. All right, so arc sine 1/2, the angle whose sine is 1/2. So the angles whose sine are 1/2 are these up here. And the angle is 30 degrees, and the real number is pi over 6. So the answer here is 30 degrees or pi over 6. All right. Now, we have a little dilemma in this situation. We know that the sine of 120 degrees is the square root of 3 over 2. And in radian measure, the sine of 2 pi over 3 is the square root of 3 over 2. Now, you see, it's the idea that we have the square root of 3 over 2 here, but when we took the inverse sine of the square root of 3 over 2, we're looking for the angle whose sine is the square root of 3 over 2. Why didn't we name 120 degrees? Why didn't we name 2 pi over 3? You see, those also are angles and real numbers whose sine is the square root of 3 over 2. Why don't we name those? Why did we choose these? Well, it has to do with this inverse business having a certain domain and range quality involved in them. That when we take inverse sine, we are going to get angles that are in the either fourth quadrant or the first quadrant. And I'll tell you again that we will address the situation in the other quadrants later. But when we just look at a situation like this, we're identifying angles that fall into fourth quadrant or first quadrant. So if we're talking about the sine of 210, now the sine of 210 is negative 1/2. The sine of, because the reference angle, remember, it is, let's see, from 180 to 210, oh, it's 30 degrees, and it's a 30-degree angle, reference angle in the third quadrant, so the sine is negative, so it's negative 1/2. And for the sine of 330 degrees, fourth quadrant, reference angle 30 degrees. But since it's in the fourth quadrant, it's negative 1/2. The sine of negative 30 degrees, fourth quadrant angle, negative 1/2. So when we are requested to find the arc sine of negative 1/2, the angle whose sine is negative 1/2, gee, it could be any of these, couldn't it? Well, it turns out that when you pump it into the calculator, when you ask the calculator for an answer here, it's going to give you a fourth quadrant angle, and it's going to give it as a negative angle, and it turns out to be negative 30 degrees. So you try it on your calculator. You can do arc sine by inverse sine. It's the second function on sine, and then press in negative 0.5 here equals, and you'll get negative 30 degrees if you are in degree mode. If you're in radian mode, it'll be negative, well, the equivalent of pi over 6. Let's look at a couple of other inverses now, and we'll return to the calculation idea in just a little bit. First of all, for cosine x, we know that the graph looks like this, and it continues in this pattern forevermore, and so the function, the graph of the function fails a horizontal line test rather miserably, and so therefore the inverse will not be a function. We have to limit the domain in order for the inverse to be a function. Now we have a really nice, almost built-in limitation on the domain here. Remember, we want a domain or an interval over which the function takes on every value within its range, that is, every value from negative 1 to 1. And that occurs within the interval from 0 to pi. So that then will be the interval over which we define our function, and therefore will allow us to generate an inverse that will be a function. All right, so let's write that up here. We're limiting the domain to 0 to pi. So domain.
And then we have this tall one in the middle. Well, that's 1, 2.
0 is less than or equal to x is less than or equal to pi. Range.
1.
We know the range values go from -1 to 1, so it's -1 is less than or equal to y is less than or equal to 1. That's only important for us to identify aspects of the inverse, and we know to generate the inverse we're going to go through a process similar to the one that we did with the sine function, and it is that we'll have, well, I can designate, remember the designation for inverse function, it was this. I didn't use it over there for sine, but I certainly could use it, that f inverse of x is equal to inverse cosine of x. You see, it's like that, and a very customary and workable way to write it is simply that y equals inverse cosine of x. All right, here's the important thing, though, in terms of calculation and all of that kind of thing, that the domain of this inverse function corresponds with the range up here, and as expected, it's -1 is less than or equal to x is less than or equal to 1. That just means that we can only take the inverse cosine of numbers that are between -1 and 1. All right, now the range. Range corresponds to the domain of the original function, and that's 0 to pi. So our range is 0 to pi. 0 is less than or equal to the y values that come out of this, and those y values are less than or equal to pi. And what that really implies is that when we take the inverse cosine, that is, we find the angle whose cosine is x, then that angle is going to fall in the first two quadrants. And to emphasize it further, using angular measure, this is 0 is less than or equal to y is less than or equal to 180 degrees. So we're confining ourselves to the first two quadrants, you see, of our coordinate plane, or of our unit circle, if we'd like to think about it like that. Now, with tangent x, very similar kind of discussion here. This is the graph of tangent x, fails the horizontal line test. We need to limit the domain in order to have an inverse that is a function. And the limitation on the domain is this little interval. The interval from -pi/2 to pi/2. It's the same interval now that we used in dealing with the sine curve, or the sine function. Okay, so that's what we're going to do. And then we go through exactly the same discussion that we did before, using that idea. Now, but domain and range are a little different with tangent. Remember that, let's see, the domain we're limiting to -pi/2 to pi/2. But the range, y values that are on the graph, all real numbers. Because that graph just goes out of sight, up and down. Okay, here's how that'll change things on the inverse. Now the inverse we generated in exactly the same way, so y is simply the inverse tangent of x. And this is a request for the angle whose tangent is that. All right, now, from a function standpoint, domain and range. Domain corresponds with the range up here, so the domain would be all real numbers. Now, what that means is that we can take the inverse tangent of any number that we put into the calculator. You see, well, much unlike the sine and cosine idea. And for the range corresponds with the domain upstairs here, so it's -pi/2 to pi/2. And that means, as it did before, that when we take the inverse tangent of some value, either a real number or of some number, that we're going to get an angle or a real number that appears in either the fourth quadrant or the first quadrant. And if it's in the fourth quadrant, it'll be expressed as a negative value. Now that we have information about inverse trigonometric functions, let's work some problems. This problem says the inverse cosine of 1 over the square root of 2. And let's understand that this is a request for the angle whose cosine is 1 over the square root of 2. And let's see, is this a cosine value? Yes, it's vaguely familiar. Let's just say we're not using the calculator here, otherwise we could just punch this in and make the calculation. So we want to do it by hand, and if this is one of those familiar right triangle situations that we've had in the past and we can't recall it, then what we do is we slide over to the side and we sketch a couple of right triangles. Now, one of the right triangles you want to sketch right quick is the one with a 60-degree angle and a 30-degree angle. And remember, in this right triangle, the short side is opposite the small angle, so this is the 1, 2, square root of 3 situation. The other triangle you want to sketch is the one with 45-degree angles for the acute angles. And we only need information about one of them because they're kind of like the same. But at any rate, it's the 1, 1 square root of 2 situation. Now, from the perspective of what angle is it the case that the cosine of the angle is 1 over the square root of 2? That's really what is the request here. Oh, it's this one, because cosine is 1 over the square root of 2. Oh, it's 45 degrees. So we come back over here, 45 degrees, and that's our answer. Now, if we want to, we can convert this into radian measure, or we could have thought of these triangles as being measured in radians as well. Arctangent, the square root of 3, means that we're looking for the angle whose tangent is the square root of 3. So we look over here, oh, the square root of 3, there it is. And let's see, tangent is opposite over adjacent, so square root of 3 over 1. Oh, the perspective is from this angle, so the angle is 60 degrees. And once again, we could convert to radians very easily. Arc sine, square root of 3 over 2. Ah, the one that involves square root of 3 is this one. Now, from the perspective of which angle do we have the sine as the square root of 3 over 2? Now, that's opposite over hypotenuse, square root of 3 over 2. Oh, the perspective is, again, from this 60-degree angle. Let's use the calculator to find these. Arc cosine, negative 0.647. Arc cosine. Now, that means we want the angle whose cosine is this negative value. Now, we know probably at the beginning that the cosine of angles is positive in the first and fourth quadrants, but negative in second and third. And we know that in the world of inverse functions that we're talking about angles that appear only in the first and second quadrant for the inverse cosine. All right, and therefore this is going to be a second quadrant angle. Okay, because it's negative. Okay, now, to use the calculator, we do this. We press second, and then cosine. The second function on all of the trig functions are the inverses of them. So this is the inverse of the cosine. Okay, so it's like arc cosine or inverse cosine of, and then you just enter the number and press enter. And depending on the mode of your calculator, it will give you the answer in degrees or in radians. If you're in degree mode, the angle is approximately 130.3 degrees. I have it written off camera here. I'm reading it and writing it. I can't calculate these things on my own, you know. And if you're in radian mode, the calculator says that it's 2.27. For this one, for inverse tangent of negative 8.65, well, let's see. We would, once again, we would go second, just press second, and then the tangent button, enter the number, press enter, and we have our answer. Just, it's a piece of cake. So it turns out to be negative 83.4 degrees. Now the calculator is saying it's negative 83.4 degrees, and if we're in radian mode, it gives a negative value as well. And I'd like to talk about why. Why is it that we get a negative angle here? Now, it's not just because we have a minus sign right here. We had a minus sign up here, and yet these angles weren't negative. You see, why do we get a negative angle here? Well, it's because with both sine and tangent, the inverse functions give values that are in the fourth and first quadrant. We get angles that fall into the fourth or first quadrant, and those fourth quadrant angles are measured as negative angles, not as positive degree or radian measured angles. Now, if we want to convert this to a positive degree measured angle, you know, the coterminal angle with this would be found by just adding 360. And here we could add 2 pi to this one and get a positive radian measured angle. All right, consider the inverse sine of -4. And it turns out that this is kind of a trick question, that we can't really find the inverse sine of -4 because it's a request for the angle whose sine is -4. But the sine of angles is a number between -1 and 1. And this is a request outside of that interval, and therefore it's an impossibility. This problem says the cosine of arctangent 2. Now, arctangent 2 is a request for the angle whose tangent is 2. And this is the cosine of that angle whose tangent is 2. Now, it turns out that we can make this calculation even without determining the size of the angle. You see, we can do it like this. We can say, okay, I know that the angle whose tangent is 2 is an angle in a right triangle, and I can actually compose that right triangle like this. And if I'm talking about the perspective of this angle, the angle whose tangent is 2. Now, tangent is opposite over adjacent. So all I need to do is make sure that this fraction is equal to 2. So I could make this 4 over 2, or 10 over 5, or 12 over 6. But the easy thing to do is just to make it 2 over 1. And now I can find the length of this side. And once I have the length of this side, I can find the cosine of that angle. You see, without even finding the size of the angle itself. All right, I can find the hypotenuse like this. C squared is a squared plus b squared. So c squared is 2 squared plus 1 squared. C squared then is 4 plus 1, 5. C then is plus or minus the square root of 5, and we want the positive version, so it's the square root of 5 that we're after. So the square root of 5 is the length of the hypotenuse, and now the cosine of this angle is adjacent over hypotenuse, so it's 1 over the square root of 5. So this becomes 1 over root 5. And we would probably go to the trouble of rationalizing here, but the important thing is the calculation according to this request. The request here is for the angle whose tangent is 2, and once we have established the situation on a right triangle, we can find the cosine of that angle, and we do it by finding the lengths of the sides within the right triangle rather than finding the size of the angle. Here's another one. We're going to work it the same way. We're looking for the tangent of the inverse sine of -3/4. Now understand what this means. This is a request for an angle whose sine is -3/4. An angle whose sine is negative? Where does that angle fall? Well, we know with inverse functions that for the sine, the angle is either in the fourth quadrant or the first quadrant. And since the value is negative, we have a fourth quadrant angle. Fourth quadrant angle. We have a fourth quadrant right triangle, too. The situation looks like this. We're talking about an angle that falls in the fourth quadrant and a right triangle in the fourth quadrant. And let's see, the sine of this angle is -3/4. Now, -3/4, one of either the numerator or denominator is negative, but we know that the hypotenuse is always positive. And so in this opposite over hypotenuse idea, the hypotenuse is positive, so the opposite side is -3, the opposite side from the perspective of this angle. Okay, now we have two sides. We just figure the third side, and then we can calculate the tangent of the angle. All right, let's do that. We have c squared then is a squared plus b squared. The hypotenuse is 4, so this is 4 squared equals -3 squared plus b squared. This is 16, that's 9, so we have 16 minus 9 equals b squared. B squared then is equal to 16 minus 9 is 7. So b is equal to the square root of 7. And it's the positive square root because we want the distance along this positive x-axis, and so this is the square root of 7. Now, the tangent of this angle is, let's see, opposite over adjacent. It is negative 3 over the square root of 7. So we write negative 3 over the square root of 7, and we could rationalize from here if we want to. This is the cosine of the arc sine of 2x. Now, arc sine 2x is a request for an angle whose sine is 2x. Wow, we have a variable in here. Now, we have to be a little bit careful. We know that we can only take we know that the sine of angles is a number between negative 1 and 1. So 2x has to be a number between negative 1 and 1. Now, and let's limit it even further. Let's just say we're dealing with first quadrant angles, so that it just makes the problem a little easier. So let's just say that this number needs to fall between 0 and 1. Wow. If it falls between 0 and 1, that limits the values that x can have. Now, in the future, we're not going to belabor this point very much, but it's important to realize that when a variable occurs here, we have to consider the possibilities. And I have the limitations on the value of x written in this problem, and often you'll see those in your textbook as well. Sometimes we can just assume that x can't take on values that are going to cause anything funny to happen. That would be kind of okay, but we have to make sure that we have that agreement before we go into that. Okay, so anyway, x takes on values that makes things convenient here, as we can see here, and so we're looking for the angle whose sine is 2x. And once we have that angle whose sine is 2x, we can find the cosine of that angle. Well, we really don't need the sides of the angle, though, because we can calculate the sides of the triangle that has these characteristics, and we can find the cosine that way, as we have with the other problems. So here's the idea. We have a right triangle. We have an angle whose sine is 2x. Now, sine is opposite over hypotenuse, so we can just say that this is 2x over 1. You see, like that. And now we can find the length of this side. So it's, as before, c squared is a squared plus b squared. And now we have a variable involved, but it's the same process. Conceptually, it's exactly the same kind of problem. It's 1 squared then is 2x squared plus b squared. And 1 squared is 1 equals 4x squared plus b squared. So 1 minus 4x squared equals b squared. B then is the square root of this, and it's the positive square root. And because we're in the first quadrant, we're assuming all values are positive here. But it's it's the square root of 1 minus 4x squared for this value of b. And now we want the cosine of that angle, and the cosine is adjacent over hypotenuse, so it's this radical over 1, so it's simply that radical. So the cosine of the arc sine of 2x would be the square root of 1 minus 4x squared. And we write our answer somewhere out here, I guess. All right. Now think about this one. Now let's relate these two problems, but I just want to talk to you about a little concept situation here. Arc sine 2x, the angle whose sine is 2x. All right, now once we see this, we can go through this business of making the calculation. But if this is the angle whose sine is 2x, and we're taking the sine of the angle whose sine is 2x, you see, the sine of that angle is going to be 2x. It's kind of like we have a function and its inverse here, and they kind of undo one another, and we have 2x. So 2x would be the answer here. Okay, now let me change it a little bit, and let's talk about this situation. What about the cosecant of arc sine 2x? Now, this is the angle whose sine is 2x. Now, we know that the sine of that angle would be 2x. But what about the cosecant of that angle? Well, it would be the reciprocal of the sine. So this would simply be 1 over 2x. Now, we could certainly evaluate this situation in the way that we did up here. We could take this information and we could go into this right triangle situation, and then we could say, okay, what's the cosecant? The cosecant is the hypotenuse over the opposite side. You see, like that. That's really a safe way to do it, but we could also analyze it with this reciprocal notion as well. Here's another one, and once again, it's the expression right here that is becoming a little more complicated in each of these problems, but the concept is exactly the same as it has been in the past. We want the secant of the arc sine of x minus 1. Now, and let's once again assume that x doesn't take on any funny values here, and let's assume that we're in the first quadrant. We have enough complication in the problem without the further complication of funny kinds of x values. Okay, now with that in mind then, arc sine of this means the angle whose sine is that value. So we jump right into the right triangle situation. And then once we have that, we'll make the calculation for secant. Okay, so let's do that. I'm going to erase a little bit over here and slide over. We've got a right triangle, and from the perspective of this angle. Now sine, the sine of this angle is x minus 1. And we can think of it as x minus 1 over 1, a fraction situation, so that we can think about opposite over hypotenuse. So it's x minus 1 over 1, you see, for the sine of that angle. And now we want the length of this side. And so we have this calculation of c squared equals a squared plus b squared. So 1 squared equals x minus 1 squared plus b squared. So 1 equals, now expanding here, we get x squared minus 2x plus 1 plus b squared. And moving all of these terms to the other side, we have the 1 that's already over here, minus x squared plus 2x minus 1 equals b squared. Wow, 1 minus 1, they go out, so we have minus x squared plus 2x. And that's what b squared is. So b then is the square root of all of this business. So the b side is the square root of negative x squared plus 2x. Now with that in mind, we can calculate secant. The secant of that is, from this angle, you see the secant is, let's see, hypotenuse over adjacent. So it's 1 over the square root of negative x squared plus 2x. Okay, now we know that in right triangles we've got these trig ratios, and the ratios involve 2 of the sides but not all 3. And from the perspective of a single angle, we have a ratio involving 2 of the 3 sides. Does it make some sense that if we are requesting an angle by giving information about 2 of the sides, then we could request the same angle by requesting information from a different pair of 2 sides? Here's what I'm talking about. Arctangent 9 over x is a request for the angle whose tangent is 9 over x. Now there's another way to make the request for that same angle. That's what I'm suggesting here. And we can actually make a little calculation here and find the proper request if we want to use arc sine, you see, for example. Because if this is a request for the angle whose tangent is 9 over x, then in our right triangle, or in a right triangle, you see, from the perspective of this angle, then this is the angle whose tangent is 9 over x, and tangent is opposite over adjacent, so this is 9 over x. And now if we want to make the request for the same angle using sine, that is using, let's see, these 2 sides in a ratio, you see, then we have to find the length of that side. So let's see, we would do that with, and we're looking for the hypotenuse here, so c squared then is x squared plus 9 squared. C then is the square root of x squared plus 9 squared. And if this is, and I need to erase a bit here, and if this side is the square root of x squared plus 9 squared, then the request for the angle, for this angle, can be made using arc sine by saying, I'd like to know arc sine of, and it's x over square root of x squared plus 9 squared, and it's a request for exactly the same angle that we were requesting with arctangent. Here's a problem that looks a lot like the ones we've been working, but the concept is a little bit different here. We had in parenthesis in our previous problem some inverse function in here, and we had some trig function of an inverse function, and this is kind of the other way around. Now, to evaluate here, we can think, well, the sine of 45 degrees is 1 over the square root of 2, and the arc sine of 1 over the square root of 2 is a request for the angle whose sine is 1 over the square root of 2, and that angle is 45 degrees. Now, it is often thought in this situation that we have functions that are inverses of one another right here, and since they kind of undo one another, we're going to get that angle in all situations. And in many situations, that's certainly true. But consider this problem. We have the arc sine of the sine of 135 degrees. Now we have to be a little careful. That 135 degree angle, you see, is an angle that falls in the second quadrant. You see, there's the 135 degree angle. And the reference to that is a 45 degree angle in the second quadrant. Now, it's certainly true that the sine of that angle is the same as the sine of 45 degrees. It's 1 over the square root of 2. But when we take the arc sine of 1 over the square root of 2, you see, in this world of inverse functions, it's the idea that we're going to get an angle that falls in the fourth or first quadrant, and that's all that we can get. We don't get this 135 degree angle back. We get a 45 degree angle as a result of this. So it's just something that we have to be a little bit cautious about and realize that it's not always true that if we're just undoing inverses, we get the angle that appears in this position. So just be careful about that.